So it's equilibrium. Please find this section in your notes, page 138. We're going to go through the supplemental notes, and then we're going to explore this topic in some more detail. So we're doing redox equilibrium. Again, this is an equilibrium topic, meaning that it will obey the principles of equilibrium, and it will obey the Le Chatelier principle. Okay, so I hope everybody has found the page for redox equilibrium. We completed our buffers last week. So we're going to go through the information in your supplementary notes, and then I'm going to show you some stuff to help to expound on the topic to ensure that everybody understands it clearly. Welcome to everyone. And we are about to start, so make sure you found the page 138 of your supplementary notes, and we're going to start on redox equilibrium. So let's just go down to the introductory section. Now, if you have a piece of metal, for example, magnesium, in a beaker of water, there will be some tendency for the magnesium atoms to shed electrons and go into solution as magnesium ions. The electrons will be left behind on the magnesium. Some of the magnesium ions will be attracted enough so that they will reclaim their electrons and stick back to the piece of metal. In a very short time, there will be a buildup of electrons on the magnesium, and it will be surrounded in the solution by a layer of positive ions. These will tend to stay close because they are attracted to the electrons. All right, that's missing from here. Okay, let us explain what they are trying to say. They're saying if you put a piece of metal in a solution, even though they say water here, usually it is you normally try to put the magnesium in a solution that contains the ions. So if I had magnesium, I would really put it in a magnesium solution instead of putting it in water. And what they're saying is that you're naturally going to find one of the magnesium atoms are going to want to come out to become ions. So in order to become a magnesium ion, a 2+ ion, it would have to lose 2 electrons. So the 2 electrons that it loses will stay on the magnesium metal, and then the ions would leave. So after a while, you would have a lot of magnesium ions out in the solution here, and then you'll find electrons that are on the metal surface, as you're seeing here. Now, they're also saying that some of the ions are going to want to go back to the magnesium in order to become atoms again. So in order for the ions to go back to being atoms, they would have to gain electrons. So they'll pick up 2 of the electrons that are on the surface, and they will go back to becoming atoms again. So the essence of all of this is that if you put a metal in a solution of its ions, you're going to set up a dynamic equilibrium. All right, so that's the whole point of all of this. It says that a dynamic equilibrium will be established when the rate at which the ions are leaving the surface is exactly equal to the rate at which they are joining it again. At that point, there will be a constant negative charge on the magnesium and a constant number of magnesium ions present in the solution around it. So this is what is taking place in our flask. As you are seeing here, we have the magnesium solid. Some of the atoms will lose electrons to become ions, but at the same breath, some of the ions will take back the electrons to go back to being magnesium solid again. But the point is that we have set up an equilibrium in this solution. Now, as to whether or not this equilibrium is going to be more to the left or right depends on the metal, okay? So the metal itself will determine which side the equilibrium lies to, if it's going to be to the left or right. So that's the foundation of this topic, okay? So let us continue now. It says this situation would occur with all metals. All metals would do this. If you put the metal in a solution of its ions, all metals would do that. However, it occurs at different rates. Why does it occur at different rates? It's because all metals have different reactivities. That is, different tendencies to form cations and from their atoms, right? So, copper, if you did this with copper, copper is less reactive than magnesium. That means that copper forms ions less readily. And if copper were to form any ions which do break away, the copper ions are more likely to reclaim their electrons and stick back to the metal again. You will still reach an equilibrium position, but there will be less charge on the metal and fewer ions in solution. So what they're saying is that magnesium is a more reactive metal. So all metals will do this reaction, but magnesium is a reactive metal, and thus the equilibrium is to the right. So if you are a reactive metal, then for this equation here, your equilibrium is going to be more to the right. Copper though, copper is a less reactive metal. And so the equilibrium is more to the left. So I'll allow you to copy that. So all metals are able to establish this equilibrium. It's just that it depends on where the position of the equilibrium will lie. So if the metal is a very reactive metal, its equilibrium will more lie to the right, where you'll have a lot of ions and you have a lot of negative electrons on your magnesium. If you are not reactive, then you're going to tend to want to stay to the left, where you're going to have less ions being produced, less electrons on that metal. Okay? So let me allow you to copy that before I continue. All right. So now it says that in regards to the two equations, the equilibrium lies far to the right for the magnesium, but it lies to the left for the copper. Now, because the metal, so let us see, the metal has a negative charge and the ions are positive. So, because there's a difference in the positivity of the cations of the solution and the negativity of the metal, then because electrons are on the metal, then that results in something known as a potential difference. So a potential difference is when you have differences in charge, right? So because you have positive ions in the solution and you have the metal being negatively charged, that develops something known as a potential difference. Now, the magnitude of the potential difference depends on the type of metal, right? If it is a reactive metal, you will get a larger potential difference than if it's a non-reactive metal, right? So let us make a note of that. So reactive metals have a larger potential difference. Than non-reactive ones. All right. So The difference between the number of electrons you have on the metal and the positive ions in solution form the potential difference. So copper, remember that in the first place, copper didn't really want to lose any electrons to become any ions. So copper is going to have a low potential difference or a small potential difference, right? Versus the magnesium, which was ready, because magnesium was so reactive, the magnesium readily lost its electrons to become magnesium ions. So magnesium would develop a larger potential difference than copper, right? So that difference between the negative charge on the metal and the positive charge of the ions is known as the potential difference. And each metal would have its own potential difference because each metal has its own reactivity and has a different tendency to form ions. Okay. Now, with that being said, there's a point here, a very important point, but in order for you to understand that point, I need to qualify it a little bit for you. So potential difference so the potential difference of one cell cannot be measured directly. Now, we didn't go through the MCQ from last week as yet. We just started doing redox potential. I'm going to go through an MCQ. I might not be able to do it this week, but I wanted to start this topic. So I didn't go through the MCQ just yet. All right, so I was saying to you that there's a point that I needed to add to your notes, that potential difference of a cell cannot be measured directly. We can only measure the potential difference between two cells, two half cells. So for example, if we had our cell with the magnesium, so this is a magnesium system. This is known as a half cell. Now, if you wanted to know what was the potential difference that the magnesium had in its half cell, you cannot just put an electrode inside of it and measure it. There's no way to measure one half cell by itself, right? You can't do that. What you have to do is get another half cell. For example, the copper half cell. Say this was a copper half cell with the copper ions and the copper. This would be another half cell. Well, if you connected the two of them together, you are able to measure what is the difference between the two cells. So if you were to connect these two cells together with a voltmeter in between, then the voltmeter tells you the potential difference between two half cells. So the main points that I want you to get at this point is that a half cell is created most times when a metal is submerged in a solution of its own ions. What happens is that some of the atoms from the metal are going to lose electrons to go out to become ions, and the electrons are going to stay back on the metal. Eventually, over a period of time, you're going to have positive ions in solution and the metal itself is going to be negative. Now, because there's a difference in charge between the metal and the ions, that is known as a potential difference. Now, the challenge is that you cannot measure the potential difference directly. We do not have any equipment or any apparatus that we can just dip inside of this magnesium half cell and it tells us what is the potential difference in the magnesium half cell. The only thing we have is something known as a voltmeter, and a voltmeter can basically tell you what is the difference between two half cells if you connect them together. So if I got the magnesium half cell here and I connected it to the copper half cell, a voltmeter could tell me what is the potential difference between the two cells. But we don't have any machine that can just measure one half cell and tell you the potential difference of that. But that will not stop us from being able to determine what is the potential difference of a half cell, because we have found a way to get around that by designing a specific cell known as the standard hydrogen electrode that we are going to designate a value of 0. And then we are going to use this electrode to measure the potential differences of all other half cells. So let me allow you to copy that before I continue. Are you guys seeing what I'm writing? Because somebody was saying that they had a challenge on their screen. Are you now able to see the annotations that I've been making?
I can see it.
Okay. All right, so I've explained to you how a half cell develops, how a potential difference develops in a half cell, and the fact that we cannot just put an electrode in a half cell and measure the potential difference like that. The only way we can have some idea of the potential difference is if we connect two half cells together with a voltmeter, and the voltmeter will actually read the potential difference of the two cells and tell you what is the difference between them. So to get around that now, they developed something known as the standard hydrogen electrode. This electrode was designed so that it can be used to measure the potential differences of other half cells, all right? So let me see. No, so let me just make a note below this before we go back up to the diagram. So the standard hydrogen electrode is normally abbreviated as SHE. So the SHE is designed as a reference electrode. So the standard hydrogen electrode is designed as a reference electrode or half cell, and is assigned it's assigned a potential difference of 0 volts. So it is just, they designed this electrode and they said that they are going to give it a value of 0 volts. This means that when connected to another half cell, so if you connect the standard hydrogen electrode to another half cell, the voltmeter, the reading on the voltmeter gives the potential difference of that half cell. So let me allow you to copy that, and I'll go back up and look at how they designed the standard hydrogen electrode. So they're basically saying if you connect the standard hydrogen electrode, I'm going to abbreviate it like this, to another half cell with a voltmeter, for example, a copper half cell, then the voltmeter will give you a reading and it will give you the potential difference of the copper half cell. Because the standard hydrogen electrode is given a value of 0 volts. The 0 volt. So this might give us like negative 0.3 volts. So negative 0.34 volts. And that would be for the copper half cell. So to overcome the problem, so let me remind you. So we said that you cannot measure the potential difference of a half cell directly. So if you had the copper half cell, you couldn't stick any machine inside of it to see what was the potential difference. Because there's no machine that can do that. For you to get a potential difference, you have to connect two half cells together, and the voltmeter will read the difference between the two half cells and give you. So to overcome this problem, what they did is design an electrode, which is known as a standard hydrogen electrode, and gave it a value of 0 volts. So whenever you connected that standard hydrogen electrode to any other half cell, whatever reading you got on the voltmeter would basically be telling you what is the potential difference of the other half cell. So that was how they were able to come up with the potential differences for various half cells. So the standard hydrogen electrode is a reference electrode, reference half cell, or you can call it a reference electrode. And I'll soon look at how it was designed. All right, do you have this? I hope you have the annotations now and that you know the purpose of the standard hydrogen electrode. It was designed to be a reference electrode assigned a value of 0 volts so that it could be used to connect to other half cells to work out what is the potential difference of those half cells, all right? Now let's go back up now and see how the standard hydrogen electrode was designed. So it has a chamber, and you pump hydrogen gas into that chamber at 1 bar. Bar is a unit of pressure. So hydrogen is pumped in at 1 bar. The hydrogen is pumped over a platinum wire. And at the bottom of the wire is platinum itself, solid, that is covered in porous platinum. Now, inside of the beaker is a solution that has hydrogen ions of a concentration of 1 mole per dm cube. So really, it doesn't really matter what acid you place inside the beaker here, as long as it has a hydrogen ion concentration of 1 mole per dm cube. So you could put sulfuric acid. If you put 0.5 moles of sulfuric acid inside here, you would get 1 mole per dm cube, right? So for example, you could put 0.5 molar sulfuric acid, or we could put 1 molar of hydrochloric acid, and both of them would have 1 mole per dm cube of acid. So that is how the standard hydrogen electrode is designed. All right, so as long as you have an acid that has a concentration of 1 mole per dm cube of H plus ion, that is fine. So by doing this, the hydrogen gas is being pumped over the platinum wire and is being pumped over the platinum foil, and then it gets into contact with hydrogen ions that are present in the solution. Now, by doing that, an equilibrium is established inside of this mixture. So it says that as the hydrogen ion gas flows over the porous platinum, an equilibrium is set up between the hydrogen molecules and the hydrogen ions in solution. This reaction is catalyzed by the platinum. So the reaction that takes place in this container here is that the hydrogen ions can accept 2 electrons to become hydrogen gas, and vice versa, hydrogen gas can give away 2 electrons to become hydrogen ions. This is the equilibrium that is established in this standard hydrogen electrode. Now, whenever we are going to measure the potential difference of any cell, we always try to do it under standard conditions. And standard conditions are a set of conditions that have been agreed upon in the scientific community, that whenever these experiments are carried out, everybody uses the same temperature, the same pressure, the same concentrations, so that persons can get similar readings. So whenever we are doing our redox equilibrium questions, we normally use standard conditions so that we can get uniform readings. So standard conditions, it says the position of any equilibrium can be changed by changing conditions. That means that the conditions must be standardized so that you can make fair comparisons. The concentration of the hydrogen ions in solution is also important. Changing the concentration is one way of changing the position of equilibrium. So throughout this topic, all ionic concentrations are taken as being 1 mole per dm cube. What some other standard conditions that you should know is that you always work at 25 degrees Celsius or 298 kelvins. And then we use pressure at 1 bar. So those are additional standard conditions. So I want you to copy those additional conditions, right? So when you're doing these experiments, you want to make sure that you have the temperature at 225 degrees Celsius or a pressure of 298 kelvins. Your pressure should be at 1 bar. Any solution that you're using should be at 1 mole per dm cube. And these are conditions that have been agreed on all over the world, so that people can get similar results when you're doing these experiments. All right, so I'm going to pause. I'm going to show you the standard hydrogen electrode, so you see how it's designed, how it's used, before we continue. Give me a second, let me just get this video ready for you. Okay, let me address the audio problem. 1 minute. Mm, okay, not sure what is happening with the audio.
The SHG consists of platinum wire that is connected to a PT surface in contact with an aqueous solution.
All right, let me start over. Okay.
The SHG consists of platinum wire that is connected to a PT surface in contact with an aqueous solution containing 1 mH plus in equilibrium with H2 gas at a pressure of 1 atmosphere. Let's take a look and see what happens at the standard hydrogen electrode. In this hydrogen electrode, hydrogen gas is bubbled around the platinum electrode. In the molecular view, the PT surface catalyzes the oxidation of hydrogen molecules to protons or the reduction of protons to hydrogen gas. At the electrode, hydrogen gas can either be oxidized to form hydrogen ions or hydrogen ions can be reduced to form hydrogen gas. Hence, two reactions are possible at the electrode. Oxidation. H2 gives 2H plus 2E minus. Reduction. 2H plus 2E minus gives H2. This reaction is assigned a standard electrode potential E of 0.00 volt and serves as reference. As you remember, two half cells complete a voltaic cell. Let's take a close look. Here on the left, we have zinc half cell, and on the right, we have standard hydrogen electrode. The electrons are moving from zinc electrode to hydrogen electrode. So, zinc is being oxidized. The voltmeter shows that the standard cell potential of a galvanic cell consists of a SH and a Zn by Zn2 plus couple is 0.76 volt.
So what they're showing is that if you wanted to measure the potential difference of this half cell, the zinc half cell, so what you did is that you created a half cell of zinc, this dipped into some zinc nitrate. So you would know that a potential difference is going to develop in this half cell because some of the zinc atoms are going to come out to become zinc ions and leave the electrons on the surface. So the zinc electrode is going to have a negative charge and the ions are going to be positive. That's going to cause a potential difference. Well, the only way we can measure that potential difference in this half cell is if we connected it to our standard hydrogen electrode over here, which is our reference electrode. And we know that we have assigned this value of 0. So when we connect the two cells together, the voltmeter will read it and say 0.76. Now remember, the voltmeter is designed to measure the difference between two half cells. But because this cell is designated as 0, the difference between the two cells is 0.76 and this is 0. So this is really telling us that this 0.76 is the potential difference of this zinc half cell. Because this is 0, so if you minus 0 from 0.76, then you'll get back 0.76. So that is how we use the standard hydrogen electrode to measure the potential differences of other half cells. And whenever you're making, this is known as a half cell, this is another half cell, together the two of them makes a complete cell. All right. And whenever you're setting up a system like this, there's one other piece of apparatus that you normally need to include, and it's a salt bridge. So this thing right here is a salt bridge that allows ions to flow from one half cell to the next half cell. So you would connect it up. Notice that your voltmeter is connected with these clips. So one of them will be your positive electrode and the other one will be your negative electrode. All right. So the zinc is functioning as the anode, which is the negative, which is a positive electrode. and the cathode is a negative electrode, right? So you have to have two different charges. You set it up with your voltmeter and a salt bridge, and then the voltmeter is going to read the two half cells and tell you the difference. But whenever you're using the standard hydrogen electrode, it is going to be designated a value of 0. Now, looking down at the bottom of this reaction now, you see that the standard hydrogen electrode, right, can go in two directions because it is an equilibrium. So it can go with the H plus gaining the 2 electrons to become hydrogen gas, or it can go the other direction where the hydrogen gas breaks apart to give H plus and electrons. Now, the direction that the hydrogen electrode will go in depends on what it is connected to. So in this case, the zinc electrode that it was connected to, the zinc wants to be the one that gives away electrons. Zinc is a fairly reactive metal, and it has a great tendency to give away electrons. So zinc ends up being the one that is giving away electrons. So zinc is being oxidized. Now, if the half cell there is being oxidized, then it means the standard hydrogen electrode has to do the opposite reaction, which is to do reduction. All right, so whenever you're doing a redox reaction, one system has to do oxidation and the next system has to do the opposite. You cannot have both systems doing reduction and you cannot have both systems doing oxidation. You have to have them doing opposite things. So since the zinc has chosen to be the one that gives away electrons, the hydrogen now has to definitely be the one to undergo reduction. And then that completes the cell, right? So that is how the standard hydrogen electrode functions in order to measure the half cell, the potential differences for us. All right, so there's another video I'm going to show you before we continue.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 34, which is on electrochemistry. In electrochemistry, what we're doing is generating current. We're actually generating moving electrons in a reaction, or we're requiring those. And so if you don't understand what a redox reaction is, you may want to look at that video. But a great example of electrochemistry could be a lemon battery. All we're doing is inserting two pieces of metal into the lemon, and we're going to generate voltage. Now, you'd have to hook it up to a pretty sensitive voltmeter to measure that voltage, but if we hook a number of lemon batteries up in series, we could actually light a little LED. And so electrochemistry is really the study of redox reactions, and we're separating the reduction and the oxidation portion in space or time. Now, when you do that properly, you've created something called an electrochemical cell. That cell could either be a galvanic cell. It's sometimes also referred to as a voltaic cell. An example could be a battery, and that's going to generate current. Or we could have an electrolytic cell, and that's going to require current. An example could be a rechargeable battery. And so what we're doing, remember, is separating the reduction and the oxidation. In review, reduction is the gaining of electrons, and oxidation is the losing of those electrons. And what we're doing is tapping the flow of those electrons. Now, the metal is either a cathode or an anode. And a quick way to remember that is that reduction always occurs at the cathode and oxidation at the anode. Or a better way to remember that is that the consonants R and C are going to pair, and the vowels, the O and the A, are going to pair as well. And so what we can do is analyze this cell. We can break it down into its two half reactions. We could figure out the potential of those two half reactions and then simply add them together to figure out the standard potential. So how much energy that cell could produce or require if it's electrolytic. Now this would be at STP, standard temperature and pressure. And so if we have variance from that, then we could use Le Chatelier's principle to qualitatively measure what's going on. We can also measure stoichiometry in a cell. So we could use Faraday's laws to qualitative measure that as well. And so let's start with a simple demonstration. Let's say we take zinc solid and we immerse it in a copper solution. What will happen over time is we're going to get a reaction. And what you're going to find is that zinc is going to start to become an ion dissolved in the solution, and the copper is going to start to form a solid. So you'll actually form the solid copper on the outside. And so that's a redox reaction. It's reduction, it's oxidation. There's electrons flowing there, but we're not tapping any of those electrons. And so this would be that whole redox reaction. Again, we have the zinc, which is losing those electrons, and the copper, which is gaining those electrons. And so if we break it down into its two half reactions, it's going to look like this. Oxidation is where the zinc is losing its electrons, and the copper is gaining those electrons. Those are the two parts. And so in a cell, what we try to do is separate those. But before I actually show you the cell, I want to talk about the reduction potential. In other words, that's the potential energy that can really be released in a reaction like this. And so the zinc being oxidized is like a waterfall. In other words, it has energy up here and it's releasing that energy. And we could measure it as 0.76 volts. And so you could look up standard reduction potentials and you'll find a list of these for a number of different reduction and oxidation reactions. Now, the cool thing is if we run it in the other direction, then it would be negative 7.6 volts. In other words, it'd be like trying to move the water up again. It require that energy. So if we look at the reduction part, this copper gaining of electrons, it's going to have a reduction potential or an E naught of 0.34 volts. Okay, now let's actually build that cell. Let's separate the reduction and the oxidation portion. And so over here we have the anode. That's going to be where that oxidation takes place, that oxidation of the zinc. And then we have the cathode, and they're each going to be in a different solution. So right here we've got copper metal in a copper solution, and then over here we have zinc ions in a zinc, zinc solid in a zinc solution. And if we just let it sit like this, nothing will happen. In other words, it's not going to generate any voltage if we had a little voltmeter here up at the top. And the reason why is that we haven't completed the circuit. And so to do that, we're actually going to have to add a salt bridge. The salt bridge is going to be filled lots of times with a gel. In this case, we've got sodium nitrate. And what it's going to do is it's going to allow the ions to actually flow. So once we've added the salt bridge, this thing's going to turn on. And electrons are going to flow from the anode to the cathode. In other words, the electrons that are being lost in this zinc metal as the zinc becomes a zinc ion are going to travel through the wire to the cathode, where they're going to actually pick up those electrons. And so let's talk about what's going on over here on the anode. This zinc metal, this zinc solid, is actually moving off into an ion in the solution itself. As it does that, it's losing those electrons. And so it's also losing mass. In other words, this anode is going to lose mass over time. If we look over on the other side, the cathode is actually going to gain mass because that copper that's in solution is going to combine with those electrons that are coming over from the anode, and it's going to form a copper metal. And so we could see that the voltage is 1.1 volts. How did I get that 1.1 volts? I simply added up the reduction potential of those two half reactions. Now, how long is this going to occur? It's going to occur until it reaches some kind of an equilibrium, and so it won't last forever. Now, there's a Nernst equation you could use to analyze what happens if it's not really at standard potential, but that's outside the level of AP chemistry. What you should really use is Le Chatelier's principle. So what would happen, for example, if we increase the amount of zinc on the solution? That would slow this reaction. Or if we were to increase the amount of copper, it's going to speed up this reaction. What happens if we increase the temperature? That's going to speed up the chemistry. It's going to speed up this reaction, and it's going to be quicker. In other words, we're going to generate more volts than we would if it was at a cold temperature. And so you should qualitatively kind of understand how a chemical reaction, or things that would affect a chemical reaction, could convert to things that would affect this cell. Now, what's an electrolytic cell? It's really essentially the opposite of that. In this one, what we're going to do is add current. In this case, we're adding a battery on this side, and we're actually going to cause electrons to flow. Great example of this could be electroplating, when we're actually adding one metal to the other side. Another example could be rechargeable batteries. So a rechargeable battery works as you hook it up to electricity, and what it does is it acts as an electrolytic cell. It's going to store energy inside the cell. Now you unplug it from electricity, and now it becomes a galvanic cell. It can actually release energy. And so we can also use Faraday's laws to really study stoichiometry. In other words, what's happening to changes in the mass. And there are two laws. The first one is an equivalence between electricity and the mass.
All right, I'm going to stop this one here because I don't want you to get confused. What he's basically saying to us is that in electrochemistry, we have two types of cells. We have the cells that we're going to be studying now, which are called galvanic cells. Galvanic cells are cells that you use to generate electricity. So you find two half cells, put them together, and you know that they're going to generate an electric current, and you can take that electric current and you can use it to power other things, like, for example, that's what a battery does, right? So a battery is produces electricity, and you can use that electricity to power your devices. The opposite type of cell is the electrolytic cell. In an electrolytic cell, you have to be the one that gives it electrical energy for the reaction to occur. But for our purposes, we are focusing on the galvanic cell, which is the one that can generate an electric current for us. All right, so let's continue, which talks about how do we use the standard hydrogen electrode. The standard hydrogen electrode is attached to the electrode system you are investigating. For example, if you wanted to investigate a piece of magnesium in a solution of magnesium ions, then you would connect your standard hydrogen electrode, which is this, to the cell that has the magnesium containing the magnesium solution. Notice that the magnesium solution has to operate under standard conditions, so it has to be 1 mole per dm cube. You connect the standard hydrogen electrode to the magnesium with a high voltage, a high resistance voltmeter, and you connect the circuits with a salt bridge, and then the voltmeter will be able to read. Now, what is going to happen is that electrons are going to flow when you set up a cell like this. Electrons flow from the anode to the cathode to generate an electric current. So usually when you set up your cell like this, it is not, you normally put your cathode over this side here. So we normally put our cathode to the right. And we normally put our anode over to the left. And we normally expect that electrons would flow from the left over to the right. And then the voltmeter would measure how many electrons are flowing and tell you what is the potential difference. Another thing you should know when we set up these galvanic cells is that we expect the process of oxidation to occur over at the anode side, and we expect the process of reduction to occur over by the cathode side. Remember, reduction is when you gain electrons, and oxidation is where you lose electrons. So this is the normal setup of a galvanic cell. So let me allow you to copy those annotations before I continue. All right, so I want you to understand the framework of how we set up these cells. We normally put the cathode to the right-hand side where we expect electrons to be gained. We put the anode to the left where we expect electrons to be lost. We expect the electrons that were lost from, I forgot to put in an arrow here. We expect that electrons that are being lost at the anode are going to travel through the wire, through the voltmeter, and go over to the cathode. And by doing that, Once you have a flow of electrons, you are generating an electric current, right? So let me just add that. The flow of electrons so the flow of electrons generate an electric current. So in the video that you had seen, he said that you could have done, in the video he did a reaction between zinc and copper, and he was saying that you could have actually put the zinc and copper in one container and they would react with each other. But the problem is that if you kept them in the same container, you are not going to be able to capture the electrons that were transferred from the zinc to the copper. So they're saying that if you separated the two reactions into two different containers and connected them with a piece of wire, then what you are doing is forcing the electrons to flow from one cell to the next cell. And if you can capture that flow of electrons, then you can use that flow of electrons to generate an electric current and get energy from that. So that is why you will separate the reaction into two half cells so that you can capture the energy that is being released in that reaction. Let me give you another minute to copy the annotations. All right, I'm going to move down now. To the other part where it says cells and half cells. This apparatus up here is described as a cell. It is a simple system which generates a voltage. Each of the two beakers and their contents are described as half cells. Then remember I told you that you can't complete the circuit unless you put a salt bridge. So why do we actually put a salt bridge, and how do we make a salt bridge? A salt bridge is included to complete the electrical circuit, but without introducing any more bits of metal into the system. It is just a glass tube filled with an electrolyte like potassium nitrate solution. The ends are stoppered by bits of cotton wool. This stops too much mixing of the contents of the salt bridge with the contents of the two beakers. The electrolyte in the salt bridge is chosen so that it doesn't react with the contents of either beaker. Now in this cell up here, they were saying what was it that was happening when we connected the standard hydrogen electrode to the magnesium half cell. Said that these two equilibria were set up. In the magnesium half cell we had this reaction, and in the hydrogen we had this reaction. But because magnesium has a much greater tendency to form its ions than the hydrogen ions does, the position of the magnesium equilibrium will be to the left of that of the hydrogen equilibrium. That means that there will be a much greater buildup of electrons on the piece of magnesium than on the platinum. There is a major difference between the charge on the two electrodes, a potential difference which can be measured with a voltmeter. The voltage measured would be 2.37 volts, and the voltmeter would show the magnesium as a negative electrode and the hydrogen as being positive. Right? Now this one here didn't really follow the normal convention of what should go on the left and what should go on the right. In this case, the magnesium was actually acting as the anode and the hydrogen was actually acting as the cathode, right? In this example here. But in most examples, we try to set it up in a way that we put the anode to the left and the cathode to the right. Usually that is how it is designed. But in this case, they were saying that it was really the magnesium that was doing the role of the anode. They said, what if you replace the magnesium half cell by a copper half cell? If you replace the magnesium half cell by 1 with a piece of copper, suspended in a solution containing copper ions with a concentration of 1 mole per dm cube, for example, copper sulfate solution, then copper forms its ions less readily than hydrogen does. That is, it's less reactive than hydrogen. So of the two equilibria, the copper is the one that's going to undergo reduction. So they're saying the copper will be the one that end up being reduced, and the hydrogen would end up being switched around to doing oxidation. So basically, the standard hydrogen electrode doesn't have any fixed direction that it goes in. In this case, it would be going mostly in this direction. Whereas the copper is going more, so this one is going more there. It wants to lose electrons, and the copper, on the other hand, would prefer to be going in this direction where it's accepting electrons. So the standard hydrogen electrode is one of them that can go in either directions, depending on what it is connected to. So in some instances, it will be the positive electrode. Sometimes it will be the negative electrode. It depends on what is the other cell that you have connected to. Okay. It then says there is less difference between the electrical charges on the two electrodes, so the voltage measured would be less. This time you'll only get a voltage of 0.34 volts. The other major change is that this time the copper is more positive, which is the less negative electrode. The voltmeter will show the hydrogen electrode as negative and the copper one as being positive. So what they were showing, what is basically being said here, is that the standard hydrogen electrode can become the positive electrode or the negative electrode depending on what it is connected to. And they are showing you that when you had connected the standard hydrogen electrode to the magnesium, you would have gotten a voltage of 2.37, but when you put copper, you only get a voltage of 0.34. This is basically telling you that the cell with magnesium generates more electricity than when you use copper. You'd get more energy from using magnesium than the copper. A greater voltage, meaning that it has a greater potential to do more work. All right, so I'm going to pause here now, guys, and give you a 10 minutes break before I continue to look at electrode potential. So 10 minutes time, we will resume. I'm going to go through a little bit more of the redox equilibrium before I look at the MCQ that I had asked you guys to do. So I'll do that in the latter part. I also hope to advise you about making a study schedule from now for your CAPE exam. So I'll talk about that at the end. All right, let me just continue this, and then in the last part of the class, we'll go to the MCQ. I hope most of you guys tried the questions because I sent it to you in advance so that it would be a quick process for us to go through it. All right, so this tells us about the voltmeter that we use in our circuit to measure the amount of potential difference between the two cells. So the voltmeter, a high resistance voltmeter, is used in order to avoid any flow of current through the circuit. If there was a low resistance in the circuit, electrons would flow from where there was a lot of them around the magnesium, for example, to where there are less of them on the hydrogen electrode, and the voltage would decrease. It is important to measure the maximum possible voltage in any situation. This is known as the electromotive force, and the electromotive force of a cell measured under standard conditions is known as the cell potential, which is what the voltmeter reads, between the voltage between the two cells. Now, there has been a method developed in order to draw a cell without having to draw out the beakers and so on. And these are known as cell diagrams. So it's an abbreviated way method of representing a cell. So an abbreviated way of representing all right, so instead of, if I ask you to draw a cell with the hydrogen electrode connected to magnesium, instead of you having to draw this bulky apparatus here, draw the salt bridge and to draw out everything, they have developed a summarized way for you to do it, which is known as a cell diagram. So in a cell diagram, they have come up with an abbreviated method. So what they do is that they first put one half cell over here. This is a half cell. And then they use a double vertical line to represent the salt bridge. And then after that, they write the next half cell. So this portion represents the standard hydrogen electrode. And how they have abbreviated it is that they have the platinum. Then they put beside it that the platinum has the hydrogen gas flowing over it. So there's a vertical line that should have been here. So platinum, then hydrogen gas is flowing over the platinum. And it is in square brackets because it's a gas. And then this other line here, so anytime you see one single vertical line by itself, it shows that there's a boundary between two phases. Or basically what it's saying is that you're having a change of state. So if, for example, the hydrogen here is in a gaseous state, and because the hydrogen ions are in an aqueous state, then these are two different states. So a vertical line represents a change in state. So the standard hydrogen electrode is easily abbreviated by showing the platinum. Then the hydrogen gas is in square brackets because it's a gas. Then they put a line to show that you're changing from a gaseous state to an aqueous state, right? And then when you're finished with this half cell and you're moving over to the next half cell, you use a double vertical line to represent the salt bridge. And then you go over to the next half cell and then you write the magnesium ions, which are aqueous. And then you use another vertical line because you're moving over to the magnesium solid, which is a different state. So this is a simplified method that has been developed in order to draw cells. Now, usually there's also another methodology that you would also write. You would also write the substance that is donating electrons. So you'd write the one that is donating electrons first, right? So electron donators are written first. Then, let me write it better. So the substance that donates electrons normally is written first. It donates electrons. So this is what it forms after it has donated electrons. Then this one now is the electron acceptor. So it's usually written in a certain order. So you can easily see how the electrons are flowing. So you can see that the hydrogen lost electrons, the hydrogen gas lost electrons to become H+ ions, and the magnesium took up those electrons to become magnesium solid. So basically it's written in that order. And this is a more abbreviated way of showing the cell instead of having to draw out everything. So we use cell diagrams. So I'll allow you to make those annotations. And I'm going to stop here with the redox equilibrium. And we'll complete it next week. We're going to go through the MCQ that I sent you. But does anybody have any questions on what we've covered so far in the redox equilibrium? No questions? Remember that this is just the first half of it that we will do the rest of it next week, God's willing. So a question was asked if there's a specific order for you to write the cell diagram abbreviation. Yes, the order is that you write the anode first, and then the cathode is written next. So the positive electrode is usually written first. That's where oxidation occurs. And then you come over to the cathode, which is negative, as that's where reduction occurs. So that's usually the order that the cell diagram is written in. And then over at the, when you're writing at the cathode, sorry, when you're writing at the anode, the first thing you write is which one is losing, the species that is losing the electrons first. Then you write what is left after the electrons are lost. And over the cathode side, you write the species that is going to accept the electrons first, and then you write what it forms after. Remember, the double vertical line represents the salt bridge. Remember, a single line represents a change of state. Next week, you'll see other cell diagrams where you don't have a change of state. You might have two ions which are aqueous. So you might have a Fe2 plus aqueous and a Fe3 plus aqueous. And because they are both in the same state, you can't put a vertical line between them. In those cases, you have to put a comma. So whenever two substances are in the same state, then it's a vertical line. So whether we're using an electrolytic cell or a voltaic cell, the general consensus is that the anode is a positive electrode. Should be half. And the cathode is a negative electrode. Some books have it differently. Some books have switched it around and called the negative one the anode when you're dealing with the voltaic cell. But to avoid confusion, it's the same thing that you learned with electrolysis. When you did electrolysis, you learned about the anode and the cathode. It's the same anode and cathode here. It's just that in this case, in electrolytic cell, you had to be the one who provided electric current. In this case, this cell will generate an electric current for you. That's the only difference between the two types of cells. Okay, so to avoid the confusion, I wanted to stay as the same anode and cathode that you learned in electrolysis. I have seen where, yes, the books have switched it around sometimes, but I have done quite a lot of research on it. And in most settings that I have researched it in, they said that you can still use the same definition that you use when you're doing electrolysis. You don't need to change the names of the anode and cathode. You just need to know that this is a voltaic cell versus it being an electrolytic cell. So we will use the same notations for now, okay? But you might see it in other textbooks or other areas where it's done differently. But I'll try to teach you how to navigate your way, even if they switch it around on you. All right, with that being said now, guys, I'm going to go to that MCQ paper that I had sent you. On the strong acids and the weak acids. I'm gonna put up in a minute. I really do hope everybody went through the paper because I'm expecting that it should go quickly. All right, so this, you should be seeing the paper now on the screen. All right. And I really do hope you actually spend the time to work it out so that you guys can supply me with the answers. So let us start with this paper. As I said, next week we'll return to this redox equilibrium situation. And there is I'm going to send you some additional notes for redox equilibrium for you to read through to help you, in addition to what you have in your textbook, in your supplementary notes. I'm going to send you some additional notes as well. All right, so let's start off with this first question here. So dihydrogen phosphate ion system is an important buffer in the human body. In this system, there are two acid conjugate base pairs, What are they? So who wants to start off with this one? So one person says A and one person says B. So let's go through. This is an acid. This is donating electrons to a base. This is a conjugate base. This is a conjugate acid. All right, so more persons agree with the option for A. So this is an acid with its conjugate base, and a base with its conjugate acid. So A is the correct option. Good. Next part of the question says, a formula that can be used for the calculation of the pH of this buffer is a Henderson-Hasselbach equation. Calculate the pH of this buffer given the pKa and these concentrations. Who plugged in the values? Somebody said B. I want to know if anybody else plugged in the values and got B.
Yeah, I got B.
All right, so Carissa said she got B as well. So B it is. Okay, guys, remember it's better for you to unmute yourselves and answer. It's difficult for me to monitor the chat while doing this. So let me make sure that I allow you to be able to unmute yourselves.
Is it starting?
Well, you can unmute yourselves, right? So when you want to answer, you can unmute yourself. It's easier for me than for me to check the chat. It's difficult for me to check the chat. All right, calculate the pH of a HCl solution that has a concentration of 0.25 mole per dm cube. Of course, HCl is a strong acid, so you expect that it will dissociate to give you 1, now 1-to-1 ratio. So the hydrogen concentration is 0.25, so the negative log of 0.25 should give us what?
C.
All right, so I'm hearing C, which is 0.6. Yes. Good, good. Next one. Select the correct pH for each of the following solutions. All right, so if you had 2 mole per dm cube of nitric acid, this is a strong acid as well. That's going to give off 1 H+, so we're going to have 2 mole per dm cube of the H+. So negative log of that. Nobody worked out number 3?
C.
All right, let's go. So the log of the 2, it's difficult for even my calculator to do it. So you guys are getting a +3?
I got negative.
You got a -3? Yeah, that's fine.
B. B. That's what
you got -0.3, right?
Yes, miss.
Okay, that's fine. You can have a pH that's negative. It just means that it's very strong, less than 1. All right, what about the pH of this one now, the barium hydroxide? So basically this one here, you'd have to break it apart. You see that you're gonna get 2 OH. So your OH concentration is gonna be 2 times the 0.1. So if I were you, which would be 0.2, I would find the POH, which is find the negative log of the 0.2. And then once I have that, I subtract the POH from 14, and that's supposed to give me my pH. So did anybody do it this way? So I'm getting
B.
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 13.3. Yes. All right. This one says, what would be the pH of a mixture of 20 cm cubes of 1 mole per dm cube with 10 cm cubes of 1 mole per DM cube sodium hydroxide. So you'd have to work out the moles for this. So this would be 0.02 times 1, and this would be 0.01 times 1. So, and these things should react. So HCl and sodium hydroxide should react in a 1-to-1 ratio. So it seemed like we had more HCl than sodium hydroxide. So that means that we're going to have an excess of 0.01 times 1, which is 0.01 mole of HCl. So really and truly, we should find the negative log of that 0.01 to see what the remaining solution, what the pH of the remaining solution is going to be. So when you see a situation like this, normally an acid and a base would neutralize each other. But if you have an excess of one of them, then the excess one is the one that will determine what pH you get. So you had 10 cm cubes of the base, and that would be neutralized by the 10 cm cubes of the acid. So there's going to be an excess of 10 cm cubes of acid left over, which is going to give us 0.01 mole. So what is the answer for this now? If we find the negative log of the 0.01 mole, what do we get as the pH?
It's 2.
Huh?
2.
2?
Yes, miss.
Yeah, I'm getting 2 as well.
All right, let me see something. So 10 divided by 1000 is 0.01. So the negative log of 0.01 is 2. That's what you're getting?
Miss, shouldn't you convert that to concentration before you do the negative log?
Yeah, that's why I multiplied the volume times. That's why I multiplied the volume by the concentration.
0.01 moles, and then you divide it by the 30 centimeter cube, and then that's how I got.
That is correct. I forgot to do that because you would have been adding the 20 and the 10, so you really have a total of 0.03 as a yeah. So what did that concentration work out to be?
Let me check. 0.3333 or something like that.
0.333.
Yes, miss.
Okay, and then you found negative log of that.
Yes, miss.
Yeah, that makes sense. Thank you.
Which is C.
Okay. So yeah. So I had overlooked the fact that we had been adding two things together, so the concentration is going to change. Okay. All right. Ammonia reacts with water in a reversible reaction, which are the Bronsted-Lowry bases. So ammonia reacts with water to form ammonium and OH. Which one of these are bases? Which one are bases? So then ammonia is a base.
B.
The ammonia is a base, and so is the hydroxide ion, right? So the hydroxide ion is also a base, right? So the answer is B, as you said. Yeah, so let's continue now. So what do you get for number 5? The most likely pH of a 5 mole per DM cube HCl. So we literally just find the negative log of the 5 mole per DM cube. Was this a strong acid?
B.
B as in boy. Negative log of the 5.
C.
Guys, I'm depending on you to give me the correct answers, you know.
Miss, I got C.
I got
C.
All righty.
As in cat.
Okay. Okay. All right. Next one. This was on a similar one. Oh, something was missing from this. Did you get it with the? Was a number coming up in your copy? Oh, that means that you couldn't have answered that one, right? So for part C now, for part C, let us leave that one because we don't know what value is there. But for part C, right, if we mixed the nitric acid with the base, it's a similar situation, just like the last one, right? Where we're gonna have an extra 10 cm cubes of acid left over, and we are dividing it by 30 cm cube to find out the new mole. So it should be a similar answer to what we got in the one before.
Miss C.
So the same answer we got before should be the same
Be the
answer we get
same one
here
too.
because it's the same. They're the same values, yeah. So it should be C.
Yes, miss.
All right. Number 6, in liquid ammonia, the following equilibrium is present. Identify the Bronsted-Lowry base. Which one is the base? Which one here is the Bronsted-Lowry base? Remember, Bronsted-Lowry base is an accepts protons.
A.
Yeah, the NH2 minus, because it's going to accept the proton from this. So A is the one that is a Bronsted-Lowry base. A solution of potassium permanganate was used to determine the concentration of iron ions in solution by titrating in the presence of excess dilute sulfuric acid. Using with the potassium permanganate in the burette, the end point of the reaction is when the solution in the conical flask turns. So this is a tricky one. Permanganate, when you do a titration with permanganate would change from orange to green, right? Then no, the iron 2 would change to iron 3, and this would move from green to brown. So basically, what color would you get if you had green and brown mixed up together? So it's a mixture of brown and green that we're going to see at the end point. So the best thing we could say is that it would look orange. Then they said if insufficient acid is added, the titer value is, let's ignore this. All right, I'm going to the second part. I'm gonna leave this one as well because this is more a unit 2 question. Keep unit 2. So I'm not gonna stress you with that. All right, let's look at number 9. It says the dissociation constant of water increases as temperature increases. When the temperature increases, what will happen? So remember that water has this equilibrium here. All right, let me do it the shorter way. Now, if you increase the temperature, or this reaction, you have to know if the reaction is endothermic or exothermic to know what is the effect of temperature. So that dissociation of water, is it an exothermic or endothermic process? All right, so the natural process is exothermic, right? Wait, I'm seeing different sources. I want to know what is the enthalpy of the reaction. All right, so the forward, it is actually an endothermic reaction. So if you go in this direction, if you're going over to the right, energy is absorbed. So if you increase the temperature, you're gonna want to do, you're gonna get a right shift. That means you're gonna have more H plus and more OH ions being formed, right? So that is gonna affect your KW. So what's gonna happen is that the KW is going to increase as the temperature increases, but it will remain neutral, because once you have equal concentrations of H plus and OH, the solution will remain neutral. And the only time it would become acidic or basic is if you had an increase in one or the other, but it would remain neutral. This one now, number 10, the reaction between concentrated sulfuric acid and pure ethanoic acid is as shown below. Which one of these are Bronsted-Lowry acids?
C.
So the Bronsted, so let's see who is donating a proton. So this one accepted a proton, right? So this is a base. This one is an acid, right? This one is a conjugate, well, it accepted a proton. So this is a conjugate, it has a potential to give it away. So it's a conjugate acid. And this is a conjugate base. So then the bases would have been the ethanoic acid and the HSO4. So it would have been D. So don't, so then now, let's go to number 11. Oh, sorry, it asks for the acids. Oh, sorry. So D would have been the bases, sorry. So the question asks for the acids. So the acids would have been this one here and this one here. So it would have been C. All right, so an aqueous solution of ethanoic acid is gradually diluted. Which of the following statements is incorrect? Will the pH decrease? Will the value of the Ka be unchanged? The concentration of ethanoic acid molecules will decrease. The proportion of ethanoic acid molecules which dissociate will increase. So that looks like, this looks like the, so if you have ethanoic acid, let's work it out, and water. They're saying if you increase the water concentration, then the system is going to want to reduce it. So it's going to want to go more to the right. So it's actually going to form more HO. It's going to form more H plus. So that means that this statement is true. This is true. This is true. So D is a statement which is not true. Well, let me see. The concentration of the ethanoic acid molecules decrease. Yes, the value of the Ka is unchanged. Oh, so sorry guys, the wrong one is A. So based on what we're seeing here, the pH is not going to, yeah, you're going to get more H plus. So sorry, it is going to decrease. So is correct. So it's still, so the pH will decrease because we're producing more H plus. Ka doesn't change. The concentration of the ethanoic molecules would decrease because you're adding water. And the proportion of ethanoic acid molecules which dissociate also increases. All right. This also looks true, so I'm trying to see which one is the most incorrect one. I will stay with D. That one is a tricky one. All right, number 12. Methyl orange and phenolphthalein are both acid-base indicators in the titration of a strong acid against a weak alkali. What do we expect? What's the answer for this one, guys?
Is it D?
Methyl orange and phenolphthalein are both acid-base indicators. All right, going back to this one. So it was researched and it was found that the pH actually increases. So even though we are generating more H plus ions because we are using more water, the concentration of H plus ions are going to decrease. So that is what causes the pH to rise. So A is the one that is actually the incorrect statement. So let me just correct that. So back down to this one now. Methyl orange and phenolphthalein are both acid-base indicators in the titration of a strong acid against a weak alkali. Which one would you use? So strong acid versus weak alkali, you expect that the equivalence pH is acidic because the acid is stronger than the base. So you expect that when you're at the end point, you're going to end up with an acidic pH. So which of these would be better? Because remember, you have a table which with the different indicator reference ranges. Yeah, what's the indicator range for methyl orange? What's the pH range for it?
Isn't it like
3.1 to 4.4.
And for phenolphthalein?
8.3 to 10.
8.3 to 10. All right, so definitely we are expecting an acidic pH. So methyl orange will be more suitable. Methyl orange will more pick up the endpoint first better than the phenolphthalein. That would be too late. All right, let's do this one. Which of the following statements is true about all substances that form acidic solutions in water? One thing that we can all say is that if you're an acid, you must form hydrogen ions. Right? That's common to all acids. All acids must generate hydrogen ions. All right, number 14. Select the correct pH of nitric acid, 2 mole per dm cube. What did we have? Because we had done, all we have to do is find the negative log of the 2 mole per dm cube. Right, so we should get back the negative 0.3. All right, sodium hydroxide, 2 mole per dm cube sodium hydroxide. So we find the negative log of this, and then that's the pOH. And we subtract it from 14 to find the pH. What did we get?
It's D.
B, that's what you got? 13.7, all right.
Dog.
or dog. All right. What did you get when you found the negative log of the 2? That's the negative 0.3?
0.3.
It's negative, right?
Yes,
So
miss.
14. Okay, so that means that if we have 14 minus 0.3, then we're supposed to get 13.7, right? Oh, it's 14 minus the 0.3, right? But let's see now.
So,
That's good. That well, technically it would be 14.3, as you said. Ethanoic acid, making the usual assumptions. All right. So if we had 2 mole per dm cube of ethanoic acid making the usual assumptions, what would be the pH? So we know that the H plus concentration would be equal to the square root of Ka times HA. Okay, so what did we get for the H plus concentration? Work out the Ka times the HA concentration, see what we get, and then we find the negative log of that. So when you so 1.7 so we got 5.8. So the answer for this is 5.8 times 10 to the minus 3. So we find negative log of that. It comes out to be 2.2. All right, let's use adult 1 here, and then I want to talk to you about making your study timetable. The mixture formed when 25 cm cubes of 2 mole per dm cube sodium hydroxide is added to 50 cm cubes of 2 mole per dm cube ethanoic acid with a Ka of this. Okay, so we expect that we're going to be left back with an excess of 25 cm cubes of the 2 mole per dm cube ethanoic acid. Because 25 cm cube would have gone on to neutralize the base. So we'd be left back with 25 cm cubes of this. So when we work out the mole, this will be 0.025 times 2, which would have been 0.05 mole. Divide it by the new volume, which is 75 mils. That would give us the new concentration. Which would be 0.67 mole per dm cube of HA. So H plus would be equal to the square root of the Ka times this 0.67. And that would give us 1.1 times 10 to the negative. The negative 5. So then we find the negative log of this, and that should give us our pH. So can somebody find the negative log of that and tell me the answer, please?
Miss, it would be D.
B. Okay.
Dog.
4.8. 4.8. Okay. All right, guys, we're gonna pause. Just a few more that were left to be completed. Just want to talk to you now about making your study timetables, right? Based on the projection of this coronavirus situation, it's more than likely going to be June before you might be able to return to school. And if that is the case, then you can be looking at getting your CAPE exams in June, July, that period there. So really and truly, know that you're at home, you have to use this opportunity to study for your CAPE exams. You have to treat it as if you were going to have your exams in June. Just pretend as if you had your exams in June. And I want for you to be able to study and go through the content for all your subjects in the next 5 weeks. So if you start studying for CAPE starting Monday, the 27th of April, and you study 5 days per week, and you study each subject 2 hours per day, then by the end of May, you should have been able to cover all the objectives for each subject. Now, when you're making your study timetables, I'm going to forward to you the same things that I'm saying and the calendar for April and May. And you also should download the syllabus for each of your subjects. So for example, you are going to study chemistry today. You can, and you know that you're going to dedicate 2 hours to study chemistry. It's better to split up those 2 hours in 1 hour blocks, because usually your attention span will wane after an hour. So if I'm studying chemistry for 2 hours, I do 1 hour of chemistry, I'd break for 20 minutes, and then I do another hour. Now in those 2 hours, you're supposed to write down what objectives on your syllabus, from your syllabus, you're trying to cover in those 2 hours. And then you read the notes and make sure that you cover those objectives. So you are supposed to read through your notes as well as look at questions to say that you have studied an objective. And once you have done what you want to do for chemistry, you can highlight or tick that objective for the day. You do the same thing for biology. If you do biology, you do the same thing for physics if you do physics. But you are supposed to make your timetable in a way that you can see how you are going to be able to cover the entire syllabus in the 5-week period. Now, you're supposed to only schedule 5 days per week. I also suggest that you break up your days into 2 sessions, so you can have a morning session and an afternoon session. So what you do is to try to cover 2 subjects in your morning session and then 2 subjects in your afternoon session. So remember that each subject, you need to dedicate at least 2 hours to it. But in that 2-hour period, you're supposed to have a 20-minute break. And between subjects, you also have a 20-minute break. Now, once you have covered your 4 hours in the morning, I suggest that you take like a 3 to 4 hour break before you do the second 4 hours. In doing this, you make a more realistic schedule. Nothing that is going to make you tired or fatigued. It allows you to be productive while you can still have time to relax, right? And actually complete your objectives. So I want you to actually spend this week to make that timetable, get the syllabus for each of your subjects, go through using the syllabus and say how much objectives do you need to do per day in order to get through the syllabus by the end of May. So I want you to work on making that timetable, and I would like for you to send me the timetable in WhatsApp to let me just see how you have drafted it, so I can have a look at it and give you some feedback. But I want you to make the timetable to start next week, Monday, the 27th of April, as that is going to be the start date when you're going to start studying for CAPE. And you need to make sure that you can fit in all the objectives by the end of May. Now, if for any reason you didn't get to cover an objective during the 5-day period, then you have to leave that objective, don't shade it, don't highlight it, so you know that you didn't cover it. And then you use the weekend to do whatever you didn't get to complete in the weekday. But you really don't have to schedule weekends as study days, because those can be your off days, and plus you have extra classes on the weekends anyway. But you have to use the period of April to May to actually study for CAPE. That should they open up the system by the end of June, July, and you have exams, what you can do now is use that June period now to do a second read. And that is going to be when you're going to actually start remembering and actually increasing your performance for your CAPE exams. So I really want for you to work on those timetables, and I would love for you to send them to me by this week, Saturday. Okay? Is that clear? But I'm going to send you what I just said in the group, so that you can remember how to set up your timetable. You don't want to do it in a way that you're going to get fatigued and then you end up not doing it. So you want to give yourself breaks and do it in a way that you know you'll actually achieve things. All right. So I'm going to send it to you in addition to the chemistry syllabus and the calendars, so you can work on it and get it back to me. Remember that I'm also going to be sending you some additional notes on redox chemistry for you to read through for our next class, which next week I'm hoping to finish the topic. All right, so we're going to stop there for today. I hope you enjoy the rest of